Hi, welcome to video 9.5b, the alternating series remainder. Okay, so this is straight out of the book. For a convergent alternating series, the partial sum Sn can be a useful approximation for the sum of the series, which of course makes sense. It's an infinite series, so if it is convergent, it's the sum of all those terms ad infinitum equals a particular number. So if you wanted to approximate it, obviously if you took the first, 50 numbers, you'd get a good approximation. If you took 500, you'd get a great approximation. If you take 7, you'll get an okay approximation, but you will get an approximation. But of course, it is an approximation, which means you're going to be off by so much. That's called the error involved in using the full actual sum is approximately equal to the sum using the first so many terms. So the error involved in using S is approximately Sn is the remainder, what they call Rn. So let's say n is 10. So let's say you use the first 10 terms. So, well, obviously you're going to have some, you're going to be off. You didn't use enough terms. You didn't use all the terms. So the remainder is going to be the sum of all the terms, the infinite number of terms, minus the sum of the first 10. So this would be R10 equals S minus S10. So if you think about it, if you take all the terms and take away from that the sum of the first 10 terms, what you'll be left with, this R10, is the 11th term plus the 12th term plus the 13th term, etc., etc., etc. So here's the alternating series remainder theorem. If a convergent alternating series, and by the way, this right now is only working with alternating series and it has to be convergent. If a convergent alternating series satisfies the condition that an plus 1 is less than or equal to an, in other words, the terms are decreasing, then the absolute value of the remainder Rn involved in approximating the sum S by Sn is less than or equal to the first neglected term. So you'll notice here's this S minus Sn, they have the absolute value of it. Keep in mind it's an alternating series, so you never know if the next term is going to be a positive term or a negative term. So they're just using absolute values. So they're saying the absolute value of S minus Sn, which is equal to the absolute value of Rn, is less than or equal to an plus 1. Now, the thing I want you to understand is that when you have a series, your an plus 1 is the part attached to the negative 1 to the power. Okay, it's not the whole un, but the an, and you're going to go to the next term. So what they're saying is the absolute value of this, the remainder you have. So let me kind of write that out. Okay, so if you write it out and if you look at it this way, let's say you have summation n goes from 1 to infinity equals un. The sum of all of those terms would go on forever, plus dot, 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 right? So your un is negative 1 to the n times an, or negative 1 to the n plus 1, or n minus 1 times an. So the actual sum would equal the sum of the first 6 terms, which are these terms right here, plus the rest of those terms. The rest of those terms is what's called the remainder, and if you use the first 6 terms to approximate the series, then the remainder is called R6, and R6 actually represents the 7th term plus the 8th term plus the 9th term, etc. So what they're saying is that the sum of all the terms minus the sum of the first 6 terms, which is their S minus Sn, the absolute value of that is equal to the absolute value of the remainder of the 6 terms, right? So if I take the S minus S6, I'm left with R6. And we're saying that that is less than, the absolute value of that is less than or equal to an plus 1. Okay? So here's an example. So if we do use the first 6 terms, the absolute value of the error is going to be less than or equal to a 7th. That's not the 7th term, it's actually the absolute value of the 7th term. Notice how here I'm saying that an plus 1 is really the absolute value of un plus 1. Okay, so if you look at something like number 37, it turns out that the seventh term, so if I did this, it's S is approximately S6, and we use the first 6 terms to evaluate. I'm not showing you that here, but if I took this question and just wrote out the first 6 terms and added them together, I would get this approximation. Now, because I used the first 6 terms, the absolute value of the remainder of those 6 terms is less than or equal to the absolute value of the 7th term, or A7. So what is A7 in number 38? And let's have a look at number 38. So in number, wrong book. There you go. Don't need this book, do we? Number 38. Oh, also the wrong book. Never mind. Anyways, the formula for the term was obviously 4 over the ln of n plus 1. So the 7th term, well, the absolute value of the 7th term is 4 over the ln of 7 plus 1, which is 4 over ln 8, which is approximately 1.9236. That is the maximum that we are away from the actual sum. So the actual sum lays between this approximation that we got, 2.7067, plus or minus this remainder. So if I actually added these things up, that would mean that the actual sum is somewhere, not that this is a great example, but is somewhere between 0.7831 and 4.6303. Okay? And that's the answer given at the back of the book. So it's interesting because that's not the question. I'm going to pause for a second here and pull up the textbook. Okay, so if we do look at the book, okay, it doesn't really tell you that's how they want the answer. All it says is approximate the sum of the series by using the first 6 terms. And here's the question we were looking at right here. So this whole thing is our un. If we ignore the -1 to the part, the rest of it, the 4 over the ln of n plus 1, is actually our an. So in my opinion, approximate using the first 6 terms. In my opinion, the answer is 2.7067. What they should have said is, include in that the remainder. So once we get this answer of 2.7067, it's going to be plus or minus basically the absolute value of the 7th term, and that's how you get that answer right there. Okay, here's one. Approximate the sum of the following series by using its first 6 terms. Now again, just to review, the whole thing to the right of the summation is un, but the part of it that does not include the -1 to a power, that's your an. So writing this out, it's 1 over 1 factorial minus 1 over 2 factorial, etc. The series converges by the alternating series test. Remember, you got to make sure your terms are positive, which they are, and decreasing, which they are. And then you got to find the limit as n goes to infinity of an, which sure enough is 0. So we've been asked to use the first 6 terms. So we're going to take the first 6 terms, which is 1 minus a half plus 1/6 minus 1/24 plus 1 over 120 minus 1 over 720. So the sum of the first 6 terms is exactly this. And by the way, you are taking the minuses in there. And with a calculator of some sort, can be a 34, you get 0.63194. By the alternating series remainder, you have that the absolute value of s minus s6, which is what we use, is equal to the absolute value of r6, which is less than or equal to a7. Now a7, of course, would be 1 over 7 factorial, which is 1 over 5040. That works out to be approximately 0.002. So the actual sum lies between our approximation, that 0.63194, plus or minus this 0.0002. And that works out to be a sum somewhere between these two numbers. Now here, this is a much better one. As you can see, this is between 0.6317 and 0.6321. That's a very good approximation. Okay, in 41 through 46, it says use that theorem, the alternating series remainder theorem, to determine the number of terms. Now, the number of terms, that's what they're looking for, the number of terms, okay? So the number of terms required to approximate the sum of the convergent series, so they're telling you it's convergent, with an error of less than 0.001. Okay, so to say that the error is less than 0.001 is to tell you have 3 decimal places of accuracy. Now, there's 2 ways to do this. You can simply start listing the terms and keep going until you get to the first term that is indeed less than 0.0005. Now, I want to point out this has 2 zeros. But remember, if you're going to affect the 3rd decimal place, it's because you're looking at the 4th decimal place and seeing what's happening. So, as soon as you get to a term that is less than 0.0005, that means you will no longer be affecting the 3rd decimal place, which means you'll have an answer with an error of less than 0.001. So, if this is 3 decimal places, this has to be 3 zeros followed by a 5. And then you would simply ignore that term and all the ones that came after it and just add up the ones you have left. Now, the other way of doing this is if you look at this formula, absolute value of the actual sum of all the terms minus the sum of the first n terms is equal to the absolute value of the sum of the term we didn't use, which is etc., right? Okay, so if we use the first 6 terms to approximate the sum, then the absolute value of R6 is less than or equal to 7, which means the maximum error is less than or equal to, A7. So they want this error to be less than 0.001. You have to solve this. You'd have to find n so that Rn is less than 0.001. Okay, so here's number 42. Let's look at that. Why are these both chapter 4? Did I not just open chapter 9? Isn't this it? Yeah. Okay, so we're looking at number 42. So number 42, use the theorem to determine the number of terms required to approximate the sum of the convergent series with an error of less than 0.001. All right, so first method. List the terms until you get the first term whose absolute value is less than 3 decimal places. Remember, we want with an error of less than 0.001, so we need to go 1 place further than that. So 3 decimal places means we need 3 zeros and a 5. Okay, so here is our series right here. Okay, so if you actually wrote out the terms, be careful, it does start at 0. -1 to the 0 is positive, 2 to the 0 is 1, 0 factorial turns out it's 1. So you go up to, now I don't know how far to go, so I'm just kind of guessing here that I've gone far enough. Okay, so then you rewrite them as fractions, and then here's where you need a calculator to rewrite each one as a decimal. And you're looking for the first time you have a number that's less than 0.001. And this number right here is the first time you have a number that's less than 0.001. So you can eliminate it and all the ones to the right of it, and this will be your approximation. So if you take 1 minus 0.5 plus 0.125 minus 0.0208 plus 0.0026, you will get 0.6224. Now notice I'm going to 4 decimal places because I'd like to round my final answer off to 3. So just give yourself 1 more. And therefore, we have found out it takes 1, 2, 3, 4, 5 terms to make this happen. But this is a lot of work, and if you didn't have a calculator, you would not want to be sitting there and dividing 1 by whatever 32 times 120 is. Method 2, if they want an error of less than 0.001, that means the maximum error has to be less than 0.001, which means the absolute value of the Rn has to be less than 0.001. And the absolute value of our Rn is, if we take, for example, number 40, where the series is -1 to the n plus 1 times n over 2 to the n. So therefore, the n plus first term will be n plus 1 over 2 to the n plus 1, and we want that to be less than 0.001. So you can solve that on your TI. And you will get n equals 13.